with our next class. In today's class, we are going to discuss another very important topic under transport in plants, that is water potential. Okay, so let us start. See, first of all, potential means ability to do work, isn't it? Potential means ability to do work. So in that case, water potential would mean the free energy in the water by which water would undergo or water would do certain kind of work. Now, what kind of work can water perform after all? Water's work means movement from one region to another, isn't it? So in that case, we define water potential to be free energy of water, that is called the water potential, and it is defined as chemical potential of water or the ability of water to move from one place to another or one region to another. Is that clear? Now see, the greater the concentration of water in a system, the greater is the kinetic energy and hence water potential. The more the concentration of water, of course, then the more will be water potential. Okay. Now, also another important thing to mark here is that water always moves from a region of higher water potential to lower water potential. Alright. Now, see, water potential is always denoted by a Greek letter psi and its unit is going to be Pascal. Okay. Now, water potential hence is denoted by the sign psi W, and we refer psi W, that is water potential of pure water at standard temperature and when it is not subjected to any kind of pressure, to be 0. Okay, water potential of pure water at standard temperature and when it's not under any pressure, we regard that to be 0. Alright. Now, see, there are certain factors that are responsible for water potential to occur. Okay, that is first, when solute dissolves in water, the water concentration will reduce. You know very well that water potential is directly proportional to concentration of water, right? So whenever some solute will dissolve in water, its concentration will decrease, isn't it? And if concentration is decreasing, water potential will also decrease, isn't it? So see here, when solute dissolves in water, water potential decreases, and how much it decreases, that magnitude of reduction is known as solute potential, which we refer as psi s. Psi s is always a negative value. Why? Because if water potential of pure water is going to be 0, whenever solute is dissolving in water, water potential is reducing, isn't it? Water's concentration is reducing means water's potential is reducing. So something is reducing below 0. So of course it is going to be negative. Alright. Now, for a solution at atmospheric pressure, psi W, that is water potential, is equal to solute potential. Alright. Now, also another thing that comes into play whenever water potential is to be mentioned is called pressure potential. So see here, when water enters into an enclosed space, a positive pressure builds up in it and we refer it as psi P or pressure potential. Okay, so basically it is psi S, solute potential, or psi P, pressure potential, that together will be affecting the water potential at any given time. So that's why thus psi S and psi P are two main components that determine the water potential. Hence, they have a relation between them which is as follows. That is, psi W is equal to psi S plus psi P. So, water potential is going to be calculated as a summation of solute potential and pressure potential. Alright, understood this? So, this is all about water potential. I hope all of you are clear about it. Do remember all the relation that is associated with water potential, solute potential and pressure potential. Alright. Now, next topic that we are going to discuss is membrane permeability. See, it is the ability of a membrane to allow substances to pass through it. Whatever substances can pass through a membrane, that would be deciding its permeability. Alright. So, based on the permeability, membranes can be of 4 types. First, impermeable membrane. A membrane is called impermeable when it does not allow anything to pass through it. For example, suberile cell wall or cutinized cell walls. These are always referred as impermeable membrane. Alright. Next, permeable membrane. If a membrane allows everything to pass through it, in that case it would be referred as a permeable membrane. For example, cellulosic cell wall. It smoothly allows substances to pass through it. Alright. Next, semi-permeable membrane. Now these are the membranes which will permit the movement of solvents but will always restrict the solutes. Okay. For example, egg membrane or parchment membrane. These are the membranes which will allow solvents to pass but restrict all types of solutes. Alright. Last is selectively permeable membrane. So these are also kind of semi-permeable membrane itself, but they have a selectivity. Means they will allow certain solutes to pass and restrict the others, as if they are selecting the type of solutes that can pass through them. Hence we call them selectively permeable membrane. Our biomembrane, that is plasma membrane, or the membrane of the sap vacuole in the plant cell, that is called tonoplast. These are examples of selectively permeable membrane. Alright. I hope this is also clear. So now let us move on to the third and the last topic we are going to cover in today's class, that is osmosis. Now osmosis is something you have heard many a times. It's a very common term, right? So osmosis is a spatial type of diffusion that occurs in water through semi-permeable membrane. Okay. So in osmosis, what mainly would occur, you see, in osmosis, water would move from a region of lower solute to higher solute, or higher solvent to lower solvent, but via semi-permeable membrane. It is completely membrane dependent process. Without the semi-permeable membrane, osmosis would not take place. Alright. So see here, it is a spatial type of diffusion of water across semi-permeable membranes. It is the movement of water from a region of lower solute to higher solute through semi-permeable membrane. Now, osmosis is driven by two factors mainly. First is concentration of dissolved solutes and pressure gradient. Alright. Now, let us see a few important experiments that can demonstrate osmosis. Alright. The first is a very simple one called potato osmometer experiment. In this experiment, see, we take a clean glass jar and we fill it up with water. Now, we introduce in this jar a laterally pilled potato, which will be having a dug pit, okay, in the middle. In this pit, we will be filling sugar solution. Okay, so in that case, inside the potato there is sugar solution, outside there is water, and finally the lateral sides of the potato has been pilled so that it can allow the passage of water. Alright. So of course there is a concentration difference between the two solutions in the water and sugar solution. Of course then osmosis will take place, right? So when osmosis will take place, how will you understand osmosis is happening? See, beforehand, if I put a pin here to mark the level of sugar solution inside the potato, later on when osmosis will occur, water will move from lower solute to higher solute, means from outside towards inside the potato, isn't it? So level of sugar solution here will rise up. So if already you have marked the level of sugar solution inside the potato, later on when the level of water inside the potato would rise, you can easily understand that, right? So that way you can determine osmosis to occur. Alright. So this is a very simple experiment that you can observe, you can perform at your home as well. Now let us move on to another important experiment called thistle funnel experiment. Alright. See, thistle funnel experiment also, we take a clean glass jar, fill it up with water. So this is water, and in the water we introduce an inverted funnel. Okay, we cover the mouth of the funnel with a semi-permeable membrane and then fill up sugar solution inside the funnel. So this is sugar solution, right? So we have water outside, sugar solution inside, and in between there is a semi-permeable membrane. Of course, it is a perfect apparatus for osmosis to occur, and osmosis will be occurring in this direction, right? So water from the beaker would start entering inside the funnel. So if you have already marked the level of sugar solution beforehand, you will see that the water inside the funnel will start to rise. And as it starts to rise, you can be sure that osmosis is taking place, right? But in Thistle funnel experiment, we would like to study another important factors associated with osmosis. Like, if suppose I exert an external pressure into this inverted funnel, the amount of pressure that I will have to exert so that I can withstand the entry of water into the funnel means I would not want the level of water in the funnel to rise. For that, I will have to exert a certain amount of pressure, isn't it? The amount of pressure that you will have to exert to withstand the flow of water inside the funnel, that pressure will be regarded as osmotic pressure. And we refer it as pi. Alright. Now, as because there is a pressure being exerted in this direction, that means osmotic pressure, also there is an equal and opposite pressure being exerted in the opposite direction, right? And water is wanting to get into the beaker, that is also under a pressure, right? So this pressure that is being exerted towards the funnel, this is called osmotic potential. The potential of water to undergo osmosis. And this osmotic potential is clearly arise because of the solute dissolved in the water, right? That's what is creating the solute gradient after all, right? So in that case, this osmotic potential can be directly referred as psi s, right? So from this experiment we can observe that because psi s or osmotic potential and osmotic pressure are equal and opposite, they will nullify each other, and hence we get a relation between them that pi is equal to minus psi s. Okay, because they are both equal and opposite, so they will be equal in magnitude but opposite in sign. So that's why we can say that pi is equal to minus psi s. Alright, is that clear? So this is all about today's class. I hope all of you are clear about it. In the next class, we'll start another important topic, that is plasmolysis. Thank you.